In this video, I'm going to show you some more examples of second order and higher order linear differential equations with constant coefficient. The first example is y double prime plus y prime minus 2y equals 0, and the initial conditions are y of 0 is 4 and y prime at 0, derivative of y at the point 0, equals 1. If you remember, for solving a differential equation like this, first we have to write the characteristic equation. The characteristic equation of this differential equation is r squared plus r minus 2 equals 0. If you remember, in general, when we have ay double prime plus by prime plus cy equals 0, the characteristic equation is ar squared plus br plus c equals 0. And so, for this given differential equation, the characteristic equation is r squared plus r minus 2 equals 0. First, we have to find the solution of this characteristic equation. For solving this quadratic equation, we can simply factor this, or we can use the quadratic formula. Here, factoring this is really easy. If you want to factor this, you can write r plus 2 times by r minus 1. Note that 2 times negative 1 is negative 2, and the sum of 2 and negative 1 is positive 1. Coefficient of r is 1. So, if we factor this quadratic equation, we can write it like this. Now, if we set this equals 0 and this equals 0, from the first bracket r is negative 2, and from second bracket r is 1. So, the solution of this differential equation is y equals to c1 e to the negative 2x. Note that here we have two distinct real roots, and so the solution is something like c1 e to the root 1x plus c2 times e to the other root, second root x. If we have more root, we can continue in this form. Here we have two roots, so we have this part of the solution. So, the answer of this differential equation is c1 e to the negative 2x plus c2 e to the 1x, or simply x. And this is the solution of this differential equation. This is the general solution. But here we have initial conditions. With these initial conditions, we can find c sub 1 and c sub 2. Based on these initial conditions, if we plug in 0 in y, the value of y is 4. So we plug in 0 for x. If we plug in 0 here, e to the power of 0, not that negative 2 times 0 is 0, so the power is 0. E to the 0 is 1, so we have c sub 1 times e to the 0. E to the 0 is 1, so just c sub 1 plus c2 times e to the 0 again is 1. c sub 1 plus c sub 2 must be equal 4. Based on this initial condition, derivative of y, derivative of this, must be 1. If we take derivative of this, derivative of y is c sub 1 is a coefficient, derivative of e to the negative 2x is e to the negative 2x. Derivative of e to any expression is the same function times by derivative of the exponent. So based on this formula, derivative of e to the negative 2x is e to the negative 2x times derivative of negative 2x. But derivative of negative 2x is negative 2. You can multiply negative 2 here, or you can put negative 2 here. Plus c sub 2 times by derivative of e to the x, and derivative of e to the x is e to the x. Now here, in this function, if we plug in 0 in derivative in y prime, if we plug in 0 for x, it should equal to 1. So we have negative 2c sub 1 e to the power of 0, because x is 0, 0 times negative 2 is 0. But e to the 0 is 1, so negative 2c sub 1 plus c sub 2 times e to the 0 again is 1. It should be equal to 1. Now we have a system of equations. Two equations with two unknowns. C sub 1 and C sub 2 are unknowns. You can use different techniques for solving this system of equation. Elimination method, substitution method, and other methods. It's up to you which method you prefer. Here, I use the elimination method. If we multiply the first equation by 2, if we multiply both sides of this equation by 2, we have 2c sub 1 plus 2c sub 2 equals 8. And if we write this equation, negative 2c sub 1 plus c sub 2 equals 1. Now, by adding these two equations, if we add left side to the left side and right side to the right side, to eliminate c sub 1, by adding these two equations, if we add this to this, negative 2c sub 1 and positive 2c sub 1 cancel each other. 2c sub 1 plus 2c sub 2 plus c sub 2 is 3c2. So 3 times c sub 2 equals 8. 8 plus 1 side is 9. So from here, c2 is 3. If we divide both sides by 3, c sub 2 is 3. Now, if we plug in this c in one of these equations, it doesn't matter which one, you can find c sub 1. For example, if we plug in 3 here, c sub 1 plus 3 is 4, so c sub 1 is 1. Just move 3 to the other side, 4 minus 3 is 1. So c sub 1 is 1. Now, if we plug in 1 for c sub 1 and 3 for c sub 2 here, we can write our particular solution. Y equals to c sub 1, c sub 1 is 1. So 1 times e to the negative 2x plus 3 times e to the x. Note that c sub 2 is 3. So we plug in 3 here. So this is the solution of this differential equation. This is the final answer. Let's move to the next example. The next example is y triple prime minus 6y double prime minus 7y prime equal 0. This differential equation is of the third order because we have y triple prime. And the characteristic equation for this equation is r to the 3 minus 6r to the 2 plus 7r equals 0. For solving this equation, simply we can factor r. R is common between all terms, so we factor r. We have r squared minus 6r. Here should be minus. We have minus 7 minus 7 equals 0. Now we can factor this quadratic expression simply as r minus 7 times r plus 1. Or you can use quadratic formula for solving this quadratic equation. Now if we set this, and finally this equals 0, we have three distinct roots. R is 0, one root, r is 7, other root, and the third root is negative 1. So the solution of this differential equation is y equals to c sub 1 e to the first root 0x plus c sub 2 e to the 7x plus c sub 3 e to the third root negative 1x. Note that e to the 0 is 1, so we can simply write this as y is c sub 1. E to the 0 is 1, 1 times c1 is c1. So y equals to c sub 1 plus c sub 2 e to the 7x plus c sub 3 e to the negative x. And this is the final solution of this differential equation. Let's do another example. Y triple prime plus 9y prime equals 0. The characteristic equation here is r to the 3 plus 9r equals 0. If we factor r, we have r squared plus 9 equals 0. From here, r equals 0, or this bracket should be equal to 0. This is one simple real root. So this is a real root. But here, we cannot factor this anymore. It's a quadratic equation, but we cannot factor it. We can find r from this equation with the quadratic formula, or you can move 9 to the other side and simply you can find r. I will show you both. First, let me show you the quadratic formula. For finding r, if we want to use the quadratic formula, let me remind you very fast here, the quadratic formula. If we have ar squared plus br plus c equals 0, the quadratic formula is this: r equals negative b plus minus a square root of b squared minus 4ac over 2a. Based on this formula, if you want to solve this, note that here a is 1. We don't have any br because we don't have any r here. We have only r squared and a constant. So b is 0 in this equation, and c is this 9 here. So a is 1, b is 0, and c is 9. Don't forget this. So r equals to negative b is 0, 0 plus minus a square root of b squared. We don't have any b is 0, 0 squared is 0. Minus 4 times a times c. 4 times 1 is 4 times 9, 36. Over 2a, which is 2. A square root of 36 is 6, but we have a negative, so this equals to 0 plus minus 6i over 2. So that root of negative 36 is actually root of 36 times root of negative 1. We know that root of negative 1 is I. We'll name it I. And root of 36 is 6, so this equals 6i. Let's continue our solution. So we have 0 plus minus 6i over 2. If we divide now top by bottom, 0 over 2 is 0, plus minus 6i over 2 is 3i. So this is the solution of this quadratic equation. But the other way that you can solve this is to move 9 to the other side, equals negative 9, and take a square root. R equals plus minus a square root of negative 9. If you bring 9 out of the square root of 9 is 3, and the square root of negative 1 is I. So this equals to plus minus 3i. This is the same as this. Note that here and here we have 0 here. Exactly the same as here. Now let me remind you, when we have roots, complex roots, as when we have complex roots in the form of a plus minus bi, to conjugate complex roots, the solution of the differential equation is e to the ax times c sub 1 cosine bx plus c sub 2 sine of bx. This is the general formula for the complex roots. Here we have two complex roots. So for these two complex roots, we have to use this formula. A is 0, so a here is 0, and b is 3. Here we have 3 and here we have 3. B is 3. But note that we had here another root. So this is A and this is B. But don't forget, we have this root also. 0 is a real root. For solving and finding y here, we have a combination of two types of roots. real roots and complex roots. So we have to combine the two methods that we have learned for solving second order differential equations. When we have real roots, we use the real root formula. If you remember, the real roots, when we have real roots, we use this formula, c sub 1 e to the first root, r sub 1 x. If we have another real root, we continue like this. But we have only one real root, so we don't need any more term here. But because we have complex roots, we have to add e to the ax times c sub 1, not c sub 1, because c sub 1, we have used c sub 1 here, so let's make it c sub 2. Cosine of bx plus c sub 2 sine of bx, which here in this example r, the real root, is 0, so we have c sub 1 e to the 0x plus e to the ax. A is 0. Note that a is 0. So e to the 0x times by c sub 2 cosine of 3x plus c sub 3, not 2, sine of 3x. So this part is because of these roots, and this is because of this real root. We have only one simple real root, so we have this for that. If we simplify these e to the zeros, e to the 0 is 1. So we can write our final answer in this form, y equals c sub 1, because e to the 0 is 1. 1 times c sub 1 is c sub 1, plus e to the 0 again is 1. So we have only c sub 2 cosine of 3x plus c sub 3 sine of 3x. Let's move to another example. The given differential equation is the fourth derivative of y minus 13 second derivative of y plus 36y equals 0. Here we have a fourth order differential equation, and the characteristic equation is r to the 4 minus 13r squared plus 36 equals 0. Note that we can factor this equation by putting 2r squared here. Why instead of r we put r squared here? Because we want two terms that when we multiply them get r to the 4. So r2 times r2 works. We are looking for two numbers that multiply to 36 and the sum of them is negative 13. What are those numbers? The product of them is 36 and the sum is 13, or actually negative 13. Those numbers are negative 4 and negative 9. But note that we can factor these and this. R squared minus 4 can be written as r minus 2 times by r plus 2. And r squared minus 9 is r minus 3 times r plus 3. Note that here if instead of negative we had positive, we cannot factor it anymore. And then we have complex roots, similar to the previous question. But because here we have minus, we can factor it. From the first bracket r is 2, from second bracket r is negative 2, from third bracket r is 3, and from fourth bracket r is negative 3. So these are 4 distinct real roots. So we only need the first case. So this is only the first case of the differential equation. We have only real roots. We don't have any repeated roots or any complex roots. But we have to generalize that formula. What is the answer? What is the final answer of this differential equation? Y is c sub 1 e to the first root, c sub 2 e to the second root, c sub 3 e to the next root, and finally c sub 4 e to the last root, negative 3. So this expression is the solution of this differential equation. Let me show you one more example. The fourth derivative of y plus 25y double prime equals 0. First, as usual, we write the characteristic equation, which is r to the 4 plus 25 r squared equal 0. For solving this equation, simply we can factor r squared, and then we have this. We have to set this and this separately equals 0. From the first one, r squared is 0, and from second one, r squared plus 25 equals 0. Note that this is a quadratic equation because the degree of r is 2. But when r squared is 0, actually r times r is 0. And it is clear that r is 0, I know. But note that r equals 0, which is the root of this equation, is a repeated root because r squared is r times r. So r equals 0 is a repeated root. Don't forget this. From this equation, if we want to find r, we have to only move 25 to the other side, and then we can take a square root. Or you can use quadratic formula. But because this equation is really simple, we can move 25 to the other side. We have negative 25, and then if we take a square root, r is plus minus a square root of negative 25. A square root of negative 25 is 5i, because a square root of 25 itself is 5, but because of this negative we have I. So from this equation we get two complex roots, two conjugate complex roots. So we have a repeated root here and complex root here. So this is an example that we have combination of two cases, repeated roots and complex roots. For each one we have to use the corresponding formula. If you remember, when we have a repeated root, we use these formulas: c sub 1 e to the root plus c sub 2 x e to the root. And this is because of the repeating. When a root repeats, we multiply the first answer by an extra x. And if it repeats 3 i's, not 2 i's, here the root is repeated twice. But if the root repeats again, suppose instead of r to the 2 we have r to the 3 equals 0. Then we have to add a third term here like this, c sub 3 x2 e to the r x. And we can continue this. But here, this is enough. But for these complex roots, we have to add e to the ax times y. If you remember, this was the formula for complex roots. C sub 1, but because we have used c sub 1 and c sub 2 here, c sub 3 cosine of bx plus c sub 4 sine of b. This is the formula that we have to use here. This part is for this root, and this part is for these roots. Now, based on this formula, note that this is not a new formula, it's just combination of the two formula that we have for repeated roots and complex roots. C sub 1 e to the 0x plus c sub 2x e to the 0x, the root that is repeated, r1 is 0, plus e to the ax. A here is 0. Note that when we are finding r here, because we don't have anything here, we can suppose a is 0. So e to the 0x times c sub 3 cosine 5x plus c sub 4 sine of 5x. If we simplify this, we can write it as c sub 1 plus c sub 2x plus c sub 3 cosine 5x plus c sub 4 sine of 5x. And this is the final solution of this differential equation.